So this is lecture 5. We'll discuss further some convexity properties illustrated through examples, largely convex functions in machine learning, and then we will move towards algorithms. But to begin, let's talk about the homework exercises. I'll not discuss all the homework problems in details, but some of them, yes. Then we'll talk about remaining properties and examples of convex functions and move towards subgradient calculus and understanding the convexity of machine learning loss functions. Um, Finally, we'll discuss more convex optimization problems. So not all everything we'll cover today, but this is the trajectory we're taking. So let's begin with some homework problems. Every norm is a convex function y. Okay, so anyone had any questions or any thoughts? Why is every norm a convex function? We discussed this in this case of in the setting of convex sets. But can we just extend that proof to convex functions? Yes. So it's exactly like in the case of norm balls, right? So recap what we discussed for norm balls. I'm just pulling up the discussion from our slides. Change the zoom a bit. Okay, so let's just pull out what had um, discussed in the context of norm balls. I don't want to write that all over again. Okay, so there'll be some slight changes. We proved that norm balls are convex sets, and the idea for any 2 points x1 and x2 in the norm ball, you want to show that their convex combination also lies in the norm ball, for which we did this simple algebraic manipulation where we said lambda x1 plus 1 minus lambda x2 minus xc. I kind of rearranged it by using lambda xc plus 1 minus lambda xc to express xc itself, reorganized into lambda x1 minus xc plus 1 minus lambda x2 minus xc, and then I use this triangle inequality. So could we use the same idea here? All we need to show is this convexity, this inequality. So in fact, the problem is even simpler here, right? How would you do this?
Sir, I think we can use the fact that the domain of function is the convex set. So if we apply this triangular inequality on the domain, so we remain in the domain. And if we remain in the domain, then and if the f is convex, then that inequality holds.
Okay, so not exactly, right? I mean, the domain is always supposed to be convex. So when we moment we talk about the norm, you're actually applying it to on a convex set. So assumption is that all these so-called convex functions, right? These functions which we are trying to prove they are convex are applied on convex domain. So it's a good attempt, but the convexity of the domain doesn't necessarily imply that the function is convex. But yes, the inequality flavor is going to be similar. So what will we do? We'll say norm of, I want to show that theta x1, or let's use lambda here. Actually, let me use theta, make it different from theta x1 plus 1 minus theta x2. I want to show that this is the function at the convex combination is less than equal to the convex combinations, a convex combination of the function values, right? So this is even simpler, right? All you need to do is apply the triangle inequality. So the proof idea is similar, just that you have to do this explicitly. Clear? So it doesn't follow just because the domain is convex. Sorry, whoever suggested this, I didn't note. Could you?
So I suggested.
Yeah,
Has.
did that make sense?
Yes, sir.
Okay, let's move on to the other problem. Unless you have some questions. So um, it's important that you spend some time on the homework problem so that you're able to tune into the class quickly, even if you don't get them exactly. And then we had this other problem, right? Ellipsoid is a convex set with two equivalent forms, and we were hinting at two equivalent forms, one which involved a P inverse x minus xc transpose P inverse x minus xc. So the scaling and rotation happening through this inverse of a positive semi-definite matrix. Sorry, it's a strictly positive definite matrix. And we could also say that it's xc plus au where norm of u is less than equal to 1. You're basically shifting from xc. This is this is the xc, and what you're saying here is using this matrix A, I have scaled and kind of rotated the deviation of points from xc such that the deviation is upper bounded in norm sense by 1. So the relation, it turns out, it's basically A equals P raised to half. Right? You can do this. You can verify this. So by substituting, let's say x equals xc plus p half u. You substitute this in the expression at the top. What do you get? You can all verify. What do you get as the expression if you substitute? You get basically x minus xc transpose will be p half. Will give you basically um, x. So I said x minus xc transpose, which is nothing but p half u transpose. Get p half u transpose p inverse what's it next? It'll be p half u again, which you on expansion you'll get u transpose p half. Now this p half, p raised to half rather, because p is strictly positive definite, it's symmetric. So p half transpose p raised to half transpose is the same as p transpose raised to half, which is the same as p transpose. So you'll get basically p raised to half, p inverse p raised to half. Right? So the p inverse will get cancelled out with the p square roots of p basically, and you'll get u transpose u, right? Which is basically is going to be less than, I know, which is less than equal to 1. Okay, so but yeah, proving this will require a little bit more work. However, by substitution you can easily verify. So that's what we did now, verified by substitution. Okay.
Here we can start by replacing x with xc plus au, and then uh, put the
Right.
same in the condition, and then we'll come to say that uh, a equal to root p.
Exactly. That's what we did. So we substituted for x equal x as xc plus au. That's exactly what we did here. They're okay. I substituted here in this expression. That's how I got this. Sharat, does that help?
Yes, sir. And the idea is that the square is getting when we unwrap the square of the norm, we get like x minus xc transpose b inverse x minus x. Like
Correct.
that,
Correct.
that is suggested in the stack exchange link.
Yes. Yes. Exactly. Let's move on. There was another question I'd asked. If you could show how, if you have a function to be strongly convex defined as the function minus mu by 2 norm x square to be convex, then it's the same as saying that f is strongly convex if, along with this inequality where the function of the convex combination is less than equal to the convex combination of the function values, you're saying it's less than it by some margin. This is a margin, right? So what you get are two ways of looking at it. One is a margin based view, and the other view is an operational view. The operational view, you are saying, okay, I'll just subtract the mu by 2 norm x square, right? And the claim is that both are the same, and this becomes very handy. Now, there was a question on Teams, a very important question. Why is this relevant? I'll come to that very soon. But let's first try and show that these two are equivalent. Anyone has attempted to do this? How do you show that the two are equivalent? Okay, the idea is very simple. If you have some solution, let me know. Okay, the idea is that you'll have to basically write down this expression at the top. So let's say you have, you want to basically show that this expression is this convexity leads to this notion of strong convexity. Okay, so let's say that gx is indeed convex, right? So then what would I do? Let me write down this expression. If gx is indeed convex, then f of theta x1 plus 1 minus theta x2 by virtue of the convexity of G, I expand it in terms of f, what would I get? Is less than equal to, now I'll have some expressions, additional expressions. This plus expressions involving norm x square, I mean mu by 2 norm x square, right? So what would that yield? Minus mu by 2 norm of, on the left hand side, theta x1 plus 1 minus theta x2. This expression I'll have on the left hand side plus this one. Okay. So I'm just applying this statement. Okay, assuming this is true, what do I get? This is less than equal to our usual theta f of x1 plus 1 minus theta f of x2. But now on the right hand side, I'll have to also look at the convex combination of the function value, which is the norm value. This will give you basically minus mu by 2 theta norm x1 square minus mu by 2 1 minus theta norm x1 square. Oh, sorry, x2 square. So I'll just highlight these terms in some different color so that I can expand upon them. It'd be nice if you write down. So this part is, let's say I'm just denoting them in different colors so that I can expand upon them below. Okay, so let's try and expand the part in green or rearrange them. How do you rearrange them? You can, well, what you could do is not just rearrange but also bring some of the components from the right hand side to the left hand side. Okay, so let's try and do the following. I'm also going to bring the part in the, let me use a different color. I'll use green only for this as well. So I'm just going to put them together. Okay, I'm just going to put these together. So combining the highlighted expressions on the LHS left hand side, what do I get? So I'm going to write that down somewhere else, maybe below. Okay, so I'll have this mu by 2 theta norm x1 square, and from here I'll have a mu by 2 minus mu by 2 theta square norm x1 square. So you have to expand this, right? This will expand as theta square norm x1 square plus 1 minus theta square norm x2 square plus 2 theta into 1 minus theta x1 transpose x2. Okay, so I'm assuming I don't have to expand everything from scratch. So so the first step you'll have to do is expand. Okay, so what will that yield to? But you'll see there's a theta square from here and there's a theta from here. This minus mu by 2 when it comes on the left hand side, you'll have a plus mu by 2. So overall, sorry, will this be a minus or a plus? I think it'll just be a plus, right? Yeah, it'll be a plus. So you'll have basically minus mu by 2 theta here. Sorry, theta square plus mu by 2 theta. The whole thing into norm x square x1 square. Likewise, you rearrange the terms involving 1 minus theta square into x2 square, which will have a negative term with minus mu by 2, and then you'll have plus mu by 2 1 minus theta to norm x2 square. So I'm just clubbing them together. I'll just use a different color to underline them. So I'm combining these two terms, or rather the expansion after the quadratic after squaring in the first term. Likewise, I'm going to arrange the second term b minus mu by 2 1 minus theta square plus mu by 2 1 minus theta norm x2 square. Okay, so let's again highlight this in a different color. These two terms, I brought them together. Only the squared part of the left hand side. And then I'll have a term which comes up by virtue of the expansion of the one additional term from the expansion of the square, which is nothing but minus by 2. There'll be a 2 theta 1 minus theta absolute value of x1 transpose x2. Okay. So this is the additional term from this remaining term square expansion. When all this, now what do I do next? I'll simplify these expressions. So this expression, what happens when I simplify it? So I'll basically have this to be mu by 2, or yeah, I mean it amounts to minus, actually just mu by 2. Mu by 2, there'll be a theta into 1 minus theta norm x1 square. That's how it will be. The second term will be again likewise. It'll have 1 minus theta minus 1 minus 1, sorry, minus theta. So overall, yeah, I think this should amount to. Just correct me if I got a sign wrong, but this should again be mu by 2 theta into 1 minus theta norm x2 square. Is this correct? Okay. So with this, basically now I have another quadratic expansion. So this is basically u by 2 theta into 1 minus theta, which will come out common, right? If you let's just get the third term also in the correct scalars, I mean simplified scalars, we'll basically get mu into, or you can keep it as mu by 2 as it is, mu by 2, 2 theta 1 minus theta, right? So the whole thing, just copy as it is. So this whole expression will just become what? You'll have mu by 2 coming out, theta into 1 minus theta coming out, norm of x1 minus x2 square. This is interesting. So we've significantly simplified, but this is exactly what I get on the right hand side here, right? All this was on the left hand side. Now if we bring it back to the right hand side, you have exactly this margin term. Okay, so let me actually get the yeah. So this part. So this part, which is there in pink, is exactly the margin term. This is the margin term. Okay, I've just brought it to the right hand side. So hope you got the idea. Now we have shown that the formal definition of strong convexity has an operational view. You can also show corresponds to an operational view. You can also show the other way, right? That you can get the operational view from the formal definition of strong convexity. What is important is how it manifests in applications. So strong convexity becomes very handy in proving fast rates of convergence. The fast rates of convergence is often obtained by adding this, which is justified as a regularizer, right? So the operational view which you see here is basically addition of a regularizer, right? And it speeds up, it helps generalize, right? Which is the job of a regularizer, and also speed up convergence significantly. Okay, so let's get to the final homework, which is pretty much leading to what the discussion in the class. So if there are any questions on these homeworks, let me know. Otherwise, we'll move on. So the third homework I left for you was composition with vector functions, a particular use case. So let me remind you that we had dealt with the initial scalar version of these. We looked at exp of fx as an example, and we had looked at 1 by gx being convex if g is concave. So those were the two examples we took. So we had already seen that exp is monotone, non-decreasing and convex, and minus of log is non-increasing and convex. Okay, so but now you have slightly different forms. Let's understand how we could prove these forms. If anyone has thought about it, please let me know. Hello. This is an interesting expression that comes up in several machine learning optimization problems. So it's okay if you we spend a little bit time here. Okay, so we've already seen the one-dimensional case of these, right? We have seen that if f is convex, if a particular single g is convex, H is convex and non-decreasing. And now we have expanded this to multiple GIs.
So I think there's a problem with the sharing of the screen. So like I'm only able to see a small window instead. Okay.
So you can see anything.
I
Okay.
Sir, we could see the thing. Enter thing.
yes, now it's
You were able to see so far or no?
yes. So I mean the issue was that the screen somehow got minimized, so it
Oh,
wasn't full screen.
okay. Now it's fine.
Yes, it's fine.
Let's. So you saw this previous derivation, right? Previous screen derivation. Was that visible to everyone?
Yes, it was.
Yes, sir.
Okay. So let's do the first one. If anyone has already addressed. So this is all amounting to calculus. This is the calculus of convex function. Okay, so we saw this in the last class that if you have if f x is convex, and we are basically looking at x in a convex domain. This is how it looked like. So what we should immediately relate to is that the minus fx will be a concave function, and x continues remaining in a convex domain. Right. So the moment you add a negative sign, the function might flip from convexity to concavity, but the domain is not going to remain convex. Right? With that, we should be able to seamlessly operate between convexity and concavity. So coming back here, we say this concave, fx is concave if gi is concave and positive. Okay. Why we make this claim? How is this correct? By which of these properties does it hold?
Sir, property B.
Property B. Okay. So property B, GIs are concave, right? H is convex, the composition, and non-increasing in each argument. So let's verify this happens or not, and what was those corresponding choices. So this GI we're talking about here, the GI is concave, GIs are concave, and we are saying they are positive. The non-increasing in each argument is required for the convex function. So what is the convex function we are talking about here?
So if we take minus f of x, then it will be non-increasing in each argument and it will be convex. And since minus f of x is convex, then f of x will be concave.
Right. This is where we have to bring together the basic background I had set at the top, right? So the H is convex, right? And that here would correspond to minus log being convex and non-increasing. Minus log x is convex and non-increasing. There's only one argument it has. But now you have log of GIX, multiple GIs on which it's being applied. So as a result, if you consider minus log of gix, then you have overall h being minus log of x is convex, non-increasing in each argument, and the GIs are concave. So the overall, if you put a negative, you would have got convexity. Now without the negative, you have concavity. That's all. Okay, so that should be simple. Let me know if you have questions here. Otherwise, we'll proceed. Let's proceed to the second one. The first one is very simple, straightforward. Unless you need some more help, I'm going to leave it at that. Okay, for the second one, we need a little bit more work to be done. And I'm spending time on these because these are very realistic. So the first one, for example, is what you'd see in likelihood functions. So likelihood functions, you'd like them to be concave, and the max likelihood estimate would then therefore result in a unique solution if your function is concave everywhere, or it'll give a locally optimal solution if your function is concave in a particular region. And that so the machine learning, right, use case or instance is of likelihood function, which we often try and maximize. Let's look at the second example. Log sum x. I'd given it a name, and it's convex if GI is convex. That's what we are saying here. So which case would you use here? Well, we have exhausted B.
So we can use A. So GIX is convex, and exponent of something is also convex. So H is convex, and then we can use the weighted sum rule to say that the summation of all of these is also convex, and log is also a convex function itself, and by using again the
Log is
topmost rule.
convex. Log convex?
No, it's concave.
We just said that minus log x is convex, and log. So in the previous case, we actually made use of this, right? That minus log x is
Yes,
convex. Yeah. So
yes,
good that you attempted, but you're seeing there's a small problem here, right? The way you have applied it.
yes, right,
Very
sir.
good point. Yeah. I mean, it's good. Actually, we should attempt. We will fail. We'll make mistakes, but those mistakes are very important stepping stones to learning. So please attempt. I'm very happy that you made this observation. So there's a kind of a problem here if you apply it that way. But there's what we're going to do is we're going to define a function itself, hx. Okay, I'm going to define my function hx itself to be log sum x. Okay. So this is my now what you can define to be h and what is g, it's in your hands. So I'm saying this function, I'm claiming this is convex and non-decreasing in each argument. Okay, now how do you prove this? Proof for this best done using first principles. At least the calculus, some of the compositionality we have learned so far in calculus might not be immediately helpful. So what we'll do is if GIs are if EGI is convex, this expression is convex. And we already said that EGI x is convex, and that's it. We don't need anything more, right? If we need anything more, GIs are convex. That's it. We don't need non-increasing, because the non-decreasing nature, sorry, has been delegated to the hx part. Okay, so let's now prove this hx to be convex. To prove that hx is convex, I've given a hint. I've said that a function r, so I'm going to use r as h. Okay, a function r is convex if and only if r of x1 plus x2 by 2 is less than equal to, there must be a less than equal to 1 half rx1 plus 1 half rx2. So what we are saying is, well, a special case of convexity is good enough to show the general case. Special case is with alpha equals half. Okay. We generally been using any arbitrary alpha between 0 and 1, but we're saying, oh no, 1 alpha half is good enough. So it's like almost mid, it's called midpoint convexity. This has a informal name called midpoint convexity. The midpoint convexity is a function. Informally, what we are saying is a function is convex if and only if it is midpoint convex. Okay, the more general course on convex optimization, we would go around proving all of this. It's not at all difficult. I mean, these are intuitive. So you're saying we don't need all those alphas. We just need one alpha which corresponds to that midpoint. Okay. Okay, now how do you prove that Hx is convex using midpoint convexity? Let's do that. Log sum x. Now I'm going to spend a little time on this because log sum x is very ubiquitous in machine learning. Okay, so let's do that. So using midpoint convexity, let us prove that log sum x, I'll expand it further, is convex. Okay, that trick of log being concave doesn't help here directly, right? So we'll have to do a little bit more work, but we'll prove it by the first principle. Okay, how do we prove that? I mean, we'll also prove that this is not only convex, it's also non-increasing. Okay, that's easier. Non-increasing. That it is non-increasing easier. We'll not really spend time on that. Let's focus on the convexity. Non-increasing in each argument here. Okay. So let's try doing that. So we'll, as I said, we'll use a midpoint result here. I'll not use all the values. So let's write down the expression hx. This is okay. So what is that? Corresponding to log of sum. Now we're going to use I as an index over all the xi's. So it's actually, if you want to call it a vector, hx bar. So we are going to write down the left hand side and right hand side. Okay, so what we want to show, as I said, is okay. So we're going to have the following. Let's use a superscript for xi here because there are multiple xi's, and I need to use x1, x2 for the convex. The combination midpoint convexity result. So what we want to show is that log to show. Okay, so I'll show that log of I'll have a half here, right? Half of this expression. So the innermost is x. Okay, so innermost expression we are dealing with is x or x1i, x2i, so on. So actually, let me just keep this simple and let's write h first, and then we'll expand. Okay, what we want is x1 by 2 plus x2 by 2 is less than equal to 1 half hx1 plus 1 half hx2. Now I'm going to expand the LHS. Likewise, I'm going to expand the RHS. Okay, so let's write down the LHS. Now I'm going to actually write down the longer expression. You have log, you have sum over indices I. Okay, but now you have these indices I for x1 as well as x2. Okay, I've taken the liberty now of taking the summation inside. I mean the x1 and x2 inside, and the indices summation over I will remain outside. You'll have exp of x1 I plus sorry x1 I by 2 plus x2 I by 2. Okay, so this can be expressed as what? Now you have exp of x1 I by 2. What would that be expressed as? Summation over I of the square root of exp, right? X1I, or you can call it exp of x1 I whole raised to half, and then you can multiply with the other component exp of x2 I the whole raised to half. Is this clear so far?
Yes, sir.
So I'm going to substitute for some of these. This exp I is becoming quite complex, 1I, 2I, etc. Okay, so I'm going to basically say that x1 I by 2, let's say I just call it alpha I, right? And x2 I'll call it beta, x2 I by 2 I'll call it beta. So let me do some simplification here. Further, okay. So let exp of x1 I by 2 be basically, let's call it alpha I. Exp of x2 I by 2, I give it a name beta I. Okay. So with that, what will this be? It'll be nothing but log of summation over I of, yeah, I mean whether you call it x1 I by 2 of exp of that or exp xi x1 I raised to half, the same thing basically. So it'll just be summation of I of alpha I beta I. Okay. Let's expand the RHS similarly. So now what would you have? You'll have 1/2 log summation I of exp x1 I'm very soon we'll get back to alpha and beta here. Very simple in this case. Plus 1/2 log of, now what do you do with the second term? Well, it's the same thing. Summation over I of exp of x2 I. Okay, so the sum of the exp, can I do any simplification? Well, what any suggestions? What can I do with the half? Is there a way I can bring the half inside the log? Half of log, what does it mean?
So power half,
Log square.
Log square? No, half of a
No.
log is log of the expression.
So root,
Yeah, root
Yes.
of the expression, log of the
Yes.
square root of the expression, or right, the expression raised to half. So I can take the half inside.
Yes.
Let's take the half inside. We get log of, so but it's a summation raised to the half, right? It's not each exp. The summation raised to half. Likewise, I have the other summation also raised to half. Now, can I just multiply the two? Log of, so sum of logs is log of the product, right? So I can, I've kind of done that as well. I'm now having exp of x2i summed over all I, the whole raised to half. Okay, so just in plain words, what we have done, using log of a log x is log of a raised to x, and log of a, or log of x plus log of y log of xy. Okay, these two results we just made use of. Okay, let's continue. Now what can I do? I mean, I have, well, I can actually take the half again outside if you want. I mean, there are so many ways we can handle it. I want to basically put in back the alpha i's and beta i's, right? That's
Yes, sir. We can do exp x1i as alpha I square, and same as beta I square.
right. So what will this expand to? Log of, let's just substitute, it's alpha I
Alpha
square,
beta.
right? So this expression here you see, okay, so this expression exp is basic, exp x1i is alpha I square. That's what you're saying.
Yes, it is alpha I square. Yes, sir.
Right? And this expression is beta I square.
Beta I square. Yes. And then the two cuts off, and then it is summation of alpha into
I don't
summation
know.
of beta.
Two will it cut off? Let's be a little careful. You should write carefully. Okay, let's write this down. So you'll have a log of summation over I of alpha I, the whole raised to half, summation over I of beta I, the whole raised to half.
Sir, alpha is squared, right?
Oh, sorry, alpha I squared, beta I squared, the whole raised to half.
Then
Right.
we can use Cauchy Schwarz.
Yes. So at this point, we are saying log of summation alpha I beta I, is it less than equal to log of the summation of the alpha I squares raised to half, summation of I beta I squares raised to half? Yes, this is actually true by Cauchy Schwarz. So I mean, we have to somewhere make use of well-known inequality. Okay, so this indeed is the case. Okay, so let me just put together this part and this part. Okay, now I'm going to just lazily say this inequality holds by the Cauchy-Schwarz inequality. Well, I mean, do you need the log for the inequality? Do you need a log for the inequality? It's even without the log, right?
Yes, sir.
Okay, so let us remove the logs here. So this inequality holds because of Cauchy-Schwarz inequality. This is a Cauchy-Schwarz inequality. Right, that's what we use in norms, right? Vector norms. Yeah. Norm of A into B is less than equal to norm of A into norm of B. Okay, so we have proved this log sum x is a convex function under the using the midpoint convexity result. The Cauchy-Schwarz inequality, the one at below. And the fact that a log is monotonically increasing for positive values, positive arguments, which is the case here. We are only dealing with positive arguments. Sorry, this should have come later on. Okay. Any questions or comments? Otherwise, we'll move on.
Sir, is log sum strongly convex?
That's a good question. We've just barely managed to show convexity. Now, if you add these quadratic terms, do you think we'll have strong convexity? I mean, we'll need that quadratic gap, right?
Yes, sir.
Cauchy-Schwarz inequality, when is it equal? I mean, when does the inequality going to be giving an equality? When the alphas and the betas are the same, right?
Yes,
The alphas, yeah. So now if you have alphas and betas same, then basically saying like x1 and x2 are the same, then you have an equality. Is that a deterrent? Well, strong convexity requires them to be different, right? So it looks like it's strictly convex because the equality is only when the two are the same, right? That's what Cauchy-Schwarz says. So strict convexity seems to be holding because equality is only when they coincide. But is it strongly convex, which you require a quadratic expression? Very intuitively, it doesn't look like strongly convex because that gap, quadratic gap, may be difficult, right?
okay, sure, sir. Thanks.
Yeah, so some kind of intuition will help. So I think very good discussions we had today. So let me also write this point down. I'll just make a note. From the derivation above, or the proof above below, it appears that log sum x should be strictly convex. Equality holds in Cauchy odds only when the x1 and x2 are the same. But strong convexity, which requires a quadratic gap, looks unlikely. Okay, can we move on?
Sir.
Yes, please.
Sir, so I had a doubt, sir. I mean, so it is kind of observation. I don't know if it's correct or not. Sir, this convex function, sir, actually, sir, I mean, sir, Jensen inequality looks like a generalization of convex function
Yeah,
formulation.
right.
So
Right.
is that true?
Yes, I mean sometimes people use Jensen's inequality analogously or synonymously as convexity, convex inequality, Jensen's
Okay.
inequality. But you could think of convexity as a inequality in convexity as a special case.
Okay, sir.
Let's move on. If there are more questions, please do ask. Otherwise, we'll move on. Okay. This is very interesting. The next one, which is pointwise maximum and supremum. So we'll be going a little slow at this stage. Please let me know if you want to speed up. I don't want to rush through some of these important proofs. And we'll speed up again where we think we are going away. These are very critical machine learning instances of these specific properties that we'll show. Okay. So next is pointwise maximums and supremums. The simplest example of this is the x infinity norm, right? So if you have infinity norm, the infinity norm basically gives you the max value. If you have a vector x1 to xn, then this will correspond to the max of x1 to xn. Okay, so is this convex? Well, because norm is a convex function, you should hold. But then there are many other pointwise maximum examples. So in general, if f1 to fm are convex, linear being a special case in the case of x1 to xn, but if they are convex in general, then the max of these is also convex. Okay, so um, special cases, let's say the sum of r largest components of x. How do you prove this is convex? The sum of r largest components of x, can we write this as a max of multiple convex functions? X1 is the ith largest component of x. Okay, sorry, xi is the ith largest component of x. I should just write it as xi. X1 is the largest component of x. So how do you prove that this is convex? Well, you have to write this as, let's write this expression. Fx is what? Max of what? So imagine that I had uh, a vector with r1s, right? And I consider all permutations of that vector. So let's say let's call this x over. So V is a vector which belongs to the space of permutations of a vector of r1s. The first r1, or let me show it properly, right? This is 1, this is 1, blah blah blah. The first r are ones and then rest are all zeros. These are r1s. Okay, so if you have V, which is a permutation of these ones, and I take a max over what? Max over a dot product between the x and the V. You see, these are there are finite number of permutations of V, right? So maybe the kth permutation corresponds to Fk, which is xk transpose V or whatever, right? So this is basically what? The sum of r largest components of x. And therefore it's convex because it's a pointwise max of a finite number of linear functions. X transpose V is a linear function. Therefore it's convex. Linear functions we know are convex. Okay, does that help? There's another example, and this will actually uh, spin into another discussion on the following slide. The second is a pointwise supremum. So if fx, use a different color, yeah, if fx y is convex in x for every y in s. So you pick a point y in s and then fx becomes a convex function. Then gx is a convex function. Gx defined as a supremum over all the y's in s of fxy. And I'll be giving one example here, but in the following slides, a more elaborate example. So this is a function that returns the maximum eigenvalue of a symmetric matrix, lambda max x. So what would you say? Is this convex? Is a function of the symmetric matrix X. Is this convex? Can you write this as a pointwise supremum? Now, what is supremum? Supremum is basically dealing with an upper bound. I mean, think of it as max, but many times the max is not attainable, so it's like a tight upper bound. Okay, but here let's just restrict our attention to this example. So we were trying to see if fxy, this is a function of x and y. Now only difference is x is a matrix, and for every y you're basically picking a different x. So for every y, supremum over x, I mean for every x1 y combination this function is defined, right? And now you're saying over all the y's for a fixed x, what is the supremum or upper bound? Okay, think of this as upper bound, least upper bound. Okay, so this, if you just go by the pointwise supremum definition, that this is pointwise supremum, and by the fact that fxy is convex, if so if fxy is convex, then gx is convex. You just need to verify that xy divided by norm xy for a fixed value of y is convex. This is convex because this expression, right? Norm xy divided, this is 2 norm, okay? 2 norm divided by norm y for a fixed, or for a given y is convex. So the entire expression, this is convex, and this corresponds to your fx. Okay, is this fine? Then we'll move on to a more generalized statement about pointwise supremum, which will also get us the spectral norm, the nuclear norm, a whole bunch of other norms will come up. Yeah.
Say, is y eigenvector or any vector?
Y is any vector. Y is any vector.
Okay, sir.
Sir, the red part means that we can cast the problem of picking top k maximum k values in an array as a optimization problem.
This part at the top, yeah, finding the,
yes sir.
So the function which corresponds to the top max or the sum of the top k values, not just the, yeah, sum of the top k or r values, that happens to be a convex function. So if you, yeah, if you're trying to learn some parameters, for example, there are ranking losses, right? If you have done learning to rank, learning to learning parameters, so that the website that you get in response to a query which you click on gets always ranked above other websites, right? So that learning to rank can be cast as a convex optimization problem. Very good point. Yes. Does that help?
Yes sir. Yes sir.
Okay. So let me yeah. And before deep learning set in, convex optimization was totally the holy grail, and now, even now, it's very important, as we'll see. It is never going to be less relevant for reasons we have already been alluding to, but we'll see more. Because if you're dealing with even learning to rank with a deep network and you want to do anything with the final layer, you're actually dealing with a convex optimization problem. But if you're dealing with a deep network, you're dealing with regions of the convex or regions of convexity of the optimization problem. Good. This is very helpful discussion. Let's move on. I'll now delve a little bit more into the pointwise supremum case. So how is it that lambda max is in fact um, the supremum over y-ness of the 2 norm of x y divided by y, right? I mean, how does it turn out to be? Okay. Any guesses? How does it turn out to be the highest, the largest eigenvalue?
So a real symmetric matrix is orthogonally diagonalizable. So we just diagonalize it, and in that new basis, this xy2, the 2 norm of xy2 just becomes square root of the sum of components.
Right. So it's diagonalizable, and what happened? What happens in diagonalization?
In the new basis,
Using eigenvector, right? You're talking about
yes.
eigenvector decomposition. The you with the assumption that you have sorted the eigenvalues in decreasing order, you could do that as well, right? And now if you want to in that diagonalized form, if you want the y that is the that y which maximizes the ratio, right? Basically, you're saying the relative gain you get with respect to y, because you want to discount for unnecessary inflation in the magnitude of y. So relative gains you get by trading off within the y, you want to maximize. So this is basically, if you take the 2 norm, I mean, the other way is to look at the 2 norm, right? So, 2 norm square. So let's say I look at this, just look at this norm square. You'll basically get what? Y transpose x y. Correct? Now this x transpose x is the covariance matrix we have talked about. So remember in PCA we what happened was where we the maximization of the of a particular reconstruction or minimization of reconstruction, right? Loss was when you got the alignment of the solution with respect to the direction of maximum covariance. So recall from PCA. So what we are doing here is the lambda corresponding to the direction of maximum covariance. When we say covariance, we are talking about the covariance matrix. Sorry, direction maximum variance obtained through the quadratic expansion. On the right hand side. Okay. Any questions before I move on to the next slide? Okay, so this part, what we're talking about here. This is a quadratic expansion. Okay, let's now look at more generally. Yeah, this is what I said. It's a convex functional symmetric matrix. Let's look at more general matrix norms. Okay. In fact, you can have vector-induced matrix norms. So you have a vector x, a norm on the vector nx, and a norm of the ax for a fixed value of a. This is a vector norm. So all these are vector norms, right? We're dealing with vector norms all through here. So this is a vector norm. This is a vector norm application, and this is a vector norm application. But the supremum for non-zero values of the denominator, rather non-zero values of x, is a matrix norm. Now it's a norm. I mean, by definition, norm should be convex norm functions. But uh, let's get some insight into this. So we can spend time on the proof, but that's not the intention right now. Let's get an insight, and through that we may also get an intuition of the proof. So why is it convex always? Are there some interesting special cases? Well, first of all, it's convex because by the calculus of convex functions, it's a supremum, it's a pointwise supremum, right? Over the function nax, which is a function of a as well as x. Okay, think of this nax divided by nx as this function on the last slide, which we talked about as f a comma x, and we're doing a supremum over x. Okay, so that by that result should hold. But what is the intuition? For example, if you take n to be sorry, if the argument is identity, if you're looking at identity matrix, the norm is always going to be 1. Why? Well, n of ix is always n of x, n of x divided by n of x is always 1. So this should be clear, is irrespective of n. Okay, but let's look at non-trivial cases. The 2 norm, which is exactly what we kind of dealt with in the previous slide. So 2 norm MNA is lambda max A transpose A, the spectral norm. The dominant eigenvalue of A transpose A. Okay. Actually, I made a slight mistake. It's not the maximum eigenvalue, but we're talking about the maximum singular value. So yeah, the A transpose A is eigenvalue. I'll just make the correction in the previous slide. This is the correct statement. Okay. So this proof, this intuition we already got from PCA. Intuition is based on PCA. PCA, or you can look at, we saw the connection between PCA, singular value decomposition, eigenvalue decomposition. I will not go over that again. That we did in the second lecture itself. But let's move on to other use cases. So the next one we are saying is when we have one norm or when we have infinity norm, what happens? Okay, that's interesting. So let's look at the one on the left. One norm, and I'll explain in simple plain English what must be happening here. So when you have one norm, the first thing we need to understand is what is this NAX doing? Okay, let me also give that more generic statement, which I should have done earlier. So NAX, what is it doing? AX itself is a linear combination of columns of A, right, based on X. So NAX in general is the norm of norm as per N of linear combinations of the columns, right, and that is based on X. If you, for a fixed value of X, you're basically doing this computation. Now if the X were kind of restricted by one norm, right, when we divide by nx, we are just saying, okay, I want it to be normalized by the corresponding norm. So if you have one norm, what is the behavior of one norm? Well, one norm is basically the sum of absolute values, right, for a simple vector X. What is it doing? It's if I want a vector with just if X must be restricted to have one norm, then and I would like the linear combination, right? The norm, the one norm, linear combination of the columns A. What would I do? Well, I would like to take that X which peaks at the most important or the max entry. which has 1 only at the most important or max entry and 0 at other places, because um, it's a sum of absolute values, right? One norm is a sum of absolute values. Let me just put this one norm here. Is sum of absolute values. Unlike, you know, 2 norm, which is the sum of the so square root of the sum of the squares, right? So where should that peak be? So we are saying, well, that peak should be in that column whose one norm is the highest. Okay, so because we are dealing with a linear combination of columns, go back to this, right? Linear combination of columns, hence makes sense for the peak where the one norm is the one norm of the A is the highest. One norm of the A of A's columns is the highest. Okay, because we are taking a column sum. So what this corresponds to is exactly this, max over J of some. So this J is indexed into the columns, and you're saying I want across all of those columns that column which has the maximum norm. So pictorially what this is saying is I'm going to scan my A left to right column wise. This is my A, and I'll pick that column which has the maximum one norm. And pick only that as the one norm of the matrix. This should probably give you an insight into how exactly these are operating. Let's now look at the other case. If you have questions, please ask. Otherwise, we'll just proceed.
Sir, I have a small doubt.
Yeah, please.
So in the expression in the last line, mn of A is equal to max over J, and then summation of I equal to 1 to, it should be M, right? Just a small doubt. Summation I equal to 1 to M.
Okay, it's an M cross N matrix. Yeah. Thanks for.
Yeah, just that it was small doubt.
Thanks. Yeah, good point. I'll put it as M here. Any other? Let me just mark that in black. Any other question? A very good point. I'm happy you're making these careful observations. Let's look at the right hand side. Can you rationalize similarly what's happening in the right hand side? Okay, I'm going to just make this smaller. What's happening on the right hand side? What is infinity norm? Again, where does where would the one value, where would I like it to be distributed in if the infinity norm of a vector should be 1? Well, infinity norm corresponds to the max value. Now, by design, all the values could be max value and still I'll get the infinity norm of 1, right? So just note that for infinity norm of x1, we could have all entries x, all entries of x to be the same value, same max value. So that is what hinges here. This is hinged upon. We are saying, okay, I'm now dealing with again linear combinations of the columns of A based on x, but I will now take that linear combination basically peaks from the uniformly largest value in each entry in a row. So now instead of becoming a column, now we are looking at a row by just by virtue of the fact that of whatever infinity norm is. Okay, so here I'll have the depiction is like this. I'm going to, since I'm now dealing with linear combinations of columns of A, I'll say, well, I would really like that X. I'll pick that X where which peaks for the right value, the highest value in the corresponding to the row where the row one norm is highest. Basically, one norm of row is highest. There I would put my all my energy, and in fact I'll make the vector of X is all one. I mean, one in the sense all those values will be one. But where would it correspond to? It will correspond to where exactly the row norm, rather the one norm of a row is highest, that particular index. Okay, so let me just make this more intuitive. Thus, infinity norm matrix A benefits this particular definition of infinity norm. So vector induce. We have to be careful. Vector induce infinity norm of matrix A as defined above. I'll be very careful here. As defined above, because you're going to have an infinity norm on the entire matrix entries without vector definition, right? So we are saying this benefits from the uniformly possible largest entry. In the sorry, largest value, possible value each entry. Of course, we are not restricted to have the denominator to be 1. It could be some non-trivial value. We are saying, well, might as well take that largest value which corresponds to the row with the highest one norm. Okay, that's what it is. So max over I of j equals 1 to, oh, I think I've changed. This should be n, right? This should have been n. J equals 1 to n of aij. Okay, is this clear? I mean, these are interesting definitions. What I would like, if you're clear about this, I'd like to leave you with 2 homeworks. One, I'm going to now define a generalization of the spectral norm, okay, called the Schatten norm. The Schatten norm is a generalization. So you can look at spectral norm from the point of view of vector induced matrix norm, but there is another generalization of spectral norm, which also gives you nuclear norm, etc., which we have dealt with. If you remember, we talked about matrix completion, and that generalization is called the Schatten norm. What is this doing? It's basically taking a p norm, some p norm on the vector of singular values, okay, singular values of A, which are basically the square roots of the eigenvalues of A transpose A. Okay, so this is a generalization, and it turns out that this has special cases again. The first special case is p equals 1, which means you're taking a sum of the absolute values of the singular values. That's exactly the nuclear norm or trace norm. You might remember from lecture 2. Nuclear norm is the tightest convex lower bound of rank A. So it's, we had some intuition behind using the nuclear norm, but it turns out that that is a special case of Schatten norm, and this is also convex. All these are convex. Okay, so this you can recap. So I would like you to maybe understand what happens, for example, if p is infinity. P equals 1 is clear, is exactly this. But if p equals infinity, you get what? You get exactly the spectral norm. This the maximum singular value. That's exactly what we have shown here. Okay. Be straightforward for you to associate. So give some thought to this. This is, as I said, another generalization of spectral norm. But the real homework for you is basically you have to inspect these loss functions. Okay. And all given all the background I have said so far, please try and understand which of these are convex, which of them are concave, why are they convex. Okay. Homework, rationalize convexity or concavity or none, or neither. Why neither, right? For each of these ML loss functions. Remember, all these loss functions we have sufficiently motivated in our first two lectures. But we want to know their convexity. Okay, and I'll tell you most of them we have the answers already in terms of what we have discussed. Okay. Any other questions? Otherwise, I'll leave you with this homework. Do you have any other questions? So, I hope this format is helping, where I give some homework and we discuss at least some of these critical ones in detail in the class. So it's also giving you an exercise of how to work things out. Okay. If there are no more questions and no comments on the modality, we'll stop here and please attempt the homework. We'll meet on Monday. Right after this, I'm going to release the assignment. In fact, your assignment is very closely related to this kind of homework. So the more time you spend on such homework will be, the more you'll benefit it. I'll release the assignment one sometime maybe next week. Yeah. Thanks. Stop.
Sir, I
Yeah.
had a doubt from the previous class.
Yeah.
So can you open the, the PPT from the previous class?
Okay, so PPT from the previous class. Okay,
If possible.
Yeah, I can do that. I'll just have to stop. Just open it. Let me see. This one. This one.
Sir.
Yes. Yes.
So, sir, in the slide of sir, introduction to convex functions,
Right.
It's a convex set as of now, I think. So, in that slide of the introduction to convex functions,
Right.
So the back set. I think a couple of slides back.
Oh, so here. This is where we introduce convex functions.
Sir, where
Normals.
we had defined the
This
this
one?
slide only, sir. Sir, sir, in the third line, so shouldn't be there equality in the lambda to hold the equality in the bound also. For all
Here?
x and y.
Here
Yes,
you
sir.
mean?
Yes, sir.
Here?
Yes, sir.
Well, you don't need it because you're fine if you should, because see, for 0 and 1 you anyways have equality. Major concern is when you are outside 0 or 1, right?
So, sir, sir, if we don't have the equality over here, then how will we have the equality in the functions over there? F of lambda x plus 1 minus
But
lambda
they will
y.
hold, right? Even if you don't have the 0 equality here, for lambda equals 0, anyways we know there'll be equality here.
Okay, for
So it holds.
some combination of that. Yes, sir.
Yes, it holds by kind of trivially it holds.
Got it.
Is that okay? Yeah.
Yes, sir.
Thank
you,
you.
sir.
Please ask questions. Anyone else, or should we stop? Thanks, everyone.